I should.
Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. In fact, this is part of the great stuff. And I am super happy to have AAS Journal author Jared Goldberg with us today. Hey, Jared.
Hey, Frank.
I am doing very well on this
Oh,
September 2nd as we head into equinox coming up, 2022 as we go. But we're not quite there yet. It's still quite toasty in Phoenix. And where are you located at, Jared?
yeah. So I'm still in sunny Santa Barbara, California for the next few days before I head off to New York.
Uh,
Um,
uh, is it
but
is it is it Dr. Goldberg now?
it is Dr. Goldberg
All
now,
right.
and
Well,
it's
congratulations on that, Dr. Goldberg. That is wonderful. And where are you headed off to?
so I'm going to be joining the Flatiron Institute's Center
Very
for
good.
Computational Astrophysics
Mhm.
as a research fellow there.
Very cool. Very cool. Let's see, been hearing in the news, lots of very hot temperatures in California and some fires going in like Los Angeles and in San Diego. Is Santa Barbara doing okay? You got any fires? You picking up any of the smoke coming up from LA?
Yeah, so we haven't gotten any of the smoke yet, but I'm sure we will soon. It's about 80 degrees Fahrenheit in Santa Barbara, which is not it's toasty here, but it's not too bad. It's 104 where my girlfriend is down in the greater Los Angeles area. So it's
Yeah, quite the
yeah,
gradient. Go south.
quite the gradient.
Very cool. Very nice. And Jared, what do you like to do for research?
Yeah, so I am broadly interested in the connection between properties of stars and the properties of the light they produce when they explode.
Cool.
So I do theory. It's and trying to connect the properties of the stars to those properties of the light, and then maybe see if you can infer things about the star from looking at the light produced in the explosion.
Very nice. Very cool. And that is going to bring us to this very awesome APJ article. It's open access, people, so you can go get a copy for free. Shock breakout in three-dimensional red supergiant envelopes. And Jared, take us away.
Great. Well, thank you, Frank. So this work is kind of a follow-up, kind of an extension to a paper we published previously, creating these 3D models of red supergiants.
Okay.
So red supergiants are the very last stages of the life of a massive star. They are 1,000 times the radius of the sun, 1 billion times the volume, or something like that, 300 to 1,000 or so. So there's these really big extended things go out to the orbit of Jupiter, and they fuse heavier and heavier elements into the core until ultimately the core collapses in about a second. A shockwave forms that travels through the star over the time scale of about a day. And then we're really concerned with the in this work, we're really concerned with kind of the hour to hours of light produced right when the shockwave hits the very surface of the star,
Okay.
and
Okay.
explodes the whole thing just before it starts to expand. So really, when you can actually see it.
Yeah, right. Let it relate. Mm-hmm. Very cool.
Um,
Oh yeah, here we go.
yeah. Uh, so a lot of the work that's been done is considering, and there's a huge body of literature on looking at sort of what happens when radiation is able to escape ahead of a shock. A radiation powered shock plows through some plasma. Radiation eventually reaches a low enough optical depth that it can leave and you can see it. How long does it take to get bright? How long does that bright flash last? These are questions that have been explored in the case where it's a planar solution, or where you have a spherical shock breakout that for a little while just looks like the planar solution, but integrated over the sphere when you see different parts of the sphere, uh, and that kind of thing. But it's never been done in a realistic convective 3D red supergiant envelope. And so that's really what we wanted to see was, well, how does the picture change when you don't have a sphere or a plane, but when you have this bulbous surface,
Yeah.
this very 3D looking
Mm-hmm.
thing.
Mm-hmm. With Swiss cheese holes in the whole bit in it, right?
Yes, with Swiss cheese holes and bulbous plumes and all of that good stuff.
Dense knots and the whole 9 yards there. Very good.
Exactly. Yeah. So, So we did this using the Rad Hydro software Athena++, which
Mm-hmm.
is which we used. Yanfei Zhang was really hugely influential in setting these runs up and doing a lot of the numerical lifting. Um, and
Good.
so we used Athena with kind of solar-like properties. The two models in table one give sort of uh, these are mostly simulation box details. These are semi-global models, so they span basically 70% of the hemisphere facing us, uh,
Okay.
kind of 45 degrees to 45 degrees, and then 180,
Got it.
with an inner boundary kind of in the roughly the half radius coordinate or the third radius coordinate of the star, so
Okay.
that it's computationally tractable.
Mm-hmm.
Uh,
Mm-hmm.
and that inner boundary actually made it an interesting challenge to figure out how to actually uh, deposit this shockwave into the envelope and feed mass and energy in through this inner boundary that's already kind of halfway through the star,
Right.
which a lot of the next section is just devoted to talking about how we did that.
Yeah.
We used 1D, we assume an initially spherical shock. So that allows us to use 1D models with MESA,
Uh-huh.
which is modules for experiments in stellar astrophysics, is the 1D stellar evolution code. It's open source. It's great. Frank knows
It's great.
a whole lot about it. Um,
But
and
onward to here.
onward to here. So the these are properties of the models. Most notably is a parameter at the far right of table one, which I will get to later, which is this delta R, which is a new variable in some sense that characterizes the thickness of the outer layer, or really the radial span of the region that has large scale fluctuations.
Okay. Okay.
Um, so really, this is kind of what is the difference in the radius at the surface versus the radius also at the surface of the star,
I'm with
or
you. Mm-hmm.
the peak to valley on a mountain on this giant star.
Cool. I'm with you. Mm-hmm.
Um,
And you're using an actual opacity. Okay.
we are using an actual opacity from Opal. They are gray, which is an interesting caveat. It makes it hard to extract temperatures from our simulations for the actual photon spectrum.
Yeah.
But we can still do a pretty good job capturing. We think most of it, at least most of the physics, most of it is roughly thermalized by the time it breaks out, meaning that radiation and gas are somewhat in thermal equilibrium, and the electron scattering mostly dominates the opacity at shock breakout. So gray is probably okay
For now.
for now. Well,
We'll talk about future later.
it's it's in the works.
Yeah.
Um, so this section is all a lot about how we map this 1D shock from a spherically symmetric model into a 3D model. There are all sorts of complicated processes like the Rayleigh-Taylor instability that happen when a shock wave hits a composition gradient. So when the shock wave generated at the very core of this layered stellar structure where you have an oxygen core, an iron core, and then an oxygen neon core, and then carbon, helium, and then a hydrogen-rich envelope. As the shock propagates through that, instabilities form at each of those core boundaries.
Yeah.
We want to ignore all of that, and so there's a lot of this next section that says it's okay that we ignore all of that. So
Okay.
figure one is showing some of the differences between a full star explosion, which is the gray lines, complete with Rayleigh-Taylor mixing, or a 1D prescription for mixing via the Rayleigh-Taylor instability. The top panel is probably the least interesting. It might be more useful to show the bottom three. The top panel is kind of comparing the energetics and where the energy is distributed through the star, but we get really good agreement. The thin colored lines match well with the gray lines. The the location where we think the helium core boundary is given by the triangle on the full runs, and we chop out the entire helium core and inject energy just in the hydrogen envelope in the colored lines,
Got
which
it.
is ultimately the
Uh-huh.
scheme we use to inject the shock into the full envelope explosion. That way we get around a lot of the nastiness, these wiggles, and the reverse shock and those kinds of things.
Correct. Especially on initialization. Okay.
Especially on initialization. Oh gosh. Yeah.
Yes.
And again, and another thing to note is that the inner boundary of our simulations, of the 3D simulations,
Uh-huh.
is out at 300 to 400 solar radii.
Uh-huh.
So
Mm-hmm.
100 solar radii is the 10 to the 2 mark. 3 to 400 is a little bit to the right of that. So
Yes.
you can see the shock has already propagated through a good amount of the envelope by the time we even want to feed it into our 3D models.
Got it. Okay. Mm-hmm. Mm-hmm.
So then, so then this section is devoted to saying we can do it, we tested it, we verified it, we made sure that the shock matches fairly well with our analytic expectations for a radiation dominated shock,
Uh-huh.
traveling roughly spherically outwards.
Cool.
Um, and so the next few figures are just testing that scheme.
Uh-huh.
Uh, there were weird inner boundary effects with one scheme that we tried, but those inner boundary effects are very much, if you look in mass coordinate, they're very much at the inner boundary.
Uh,
So these plots are the density, the temperature, and the velocity of the fluid in a 1D run and an exactly equivalent 3D run. Uh, we put the spherical star in 3D,
right.
and then we ran the shock through it in that, just as a code verification,
Uh-huh.
basically.
Very
And
nice.
then the diamonds are the analytic expectations, which agree really well.
Uh-huh.
Um,
Okay, very good.
yeah. And
Yeah.
so then the next, but this we we deposited the shock down at 100 solar radii, which is not exactly feasible if the inner boundary is out at 3. So we we want to feed in mass and energy and momentum in through that inner boundary. We want to drive this shock.
Mm-hmm.
So what we did was we tracked that location in the 1D Mesa model explosion
Okay.
of a star that looks roughly similar to the star we exploded in 3D, or at least where a handful of properties that we identified were agreed pretty well.
Okay.
And then we tracked at the inner boundary location, at the 400 solar radius location, the kind of half radius coordinate, we tracked the fluid properties, the radiation flux, the density, the
Oh,
temperature, the velocity.
okay.
And then
Okay.
in in the 3D model, we took the temperature, density, and velocity at that. We first initialized a little bit of a shock from the one-dimensional profile
Mm-hmm.
just in the inner region, leaving the outer envelope intact.
Mm-hmm.
And then as a function, and then as the star evolves, we have a time-dependent inner boundary condition.
Gotcha.
So the temperature density, we enforced the temperature density and velocity fed into the inner boundary
Mm-hmm.
uh, is the same. So we're kind of driving the shock through the envelope.
Okay.
But the shock also is, it's a discontinuity. The velocity of the stuff at the shock front is just moving forward. It's
Mm-hmm.
almost a discontinuity. It's radiation powered, so there's a little bit of leeway there. But
Yep.
it's the shock is kind of plowing through on its own and kind of being fed the energy to keep doing that
Going.
through the inner boundary.
Mm-hmm. Mm-hmm.
So that's figure 3 is just showing that inner boundary condition for a few different explosion energies. So the other nice thing about this scheme, using a 1D model motivated shock, or is that it's really straightforward for me, with my experience using Mesa, to toggle the explosion energy.
Okay.
It's a matter of changing one parameter in an inlet that's inject until reach this total final energy.
Okay.
And so I can do that with a fiducial explosion energy of 8 by 10 to the 50 ergs, or 0.8 fo. I can do that with half of the energy. I can do that with double the energy. You could do it too. And you, the audience, could do it too,
Uh-huh.
with some amount of training work. And this is,
A little bit of pride. Mm-hmm.
yeah,
Cool.
this is showing just what the properties tracked at that one location are. So this,
Right.
we don't need to dwell on this figure. It's just it's our inner boundary condition for
Yep.
driving the shock in the 3D model.
Yep.
So what does this look like in the 3D model? So the figure on the left, figure 4, is another verification that when we do this driving the shock in an exactly equivalent scheme in a 1D and a sphere on the 3D grid, that we get really good agreement, and we do. The times the slight disagreement is because the time sampling of the Mesa output does not exactly match the time sampling of the Athena output, and
Okay.
so we did the best we could.
Sure.
But
Little interpolation and all.
yeah.
Good. Okay.
Um, and so then what happens when you put it in a 3D envelope? And so the next section deals a little bit with how does the shock propagate. So figure 5 would be a nice one to stare at, which is as the shock, which is each of so it's a similar figure to what we've seen before with density, temperature, and the radial velocity, the outward velocity uh, of the fluid, except now each, instead of being a line, each of these lines is some large number of radial rays. So we're looking along different lines of sight and seeing the diversity along the different lines of sight.
Right.
And so the shock wave starts, and so you can think of the thickness of the shock front in terms of how many lines can you distinguish from each other. The lines up front, in these early times labeled in these early times, the T1, yeah, 16 hours before shock breakout, or 16 hours before, not shock breakout, 16 hours before the peak in the light that you would see.
Okay.
Is T1, T2, T3, T4. T4 is at the time of peak light. And you can see in the bottom panel, in the lower panel, that it starts out moving fairly fast at 2,500 kilometers per second. It gets faster and faster as it travels, but there starts to be a little bit more of a diversity in the velocities near the shock front.
Yep.
And that leads to this growing spread in the location of where the shock front is, such that even at the time of peak light, the line labeled D, the thickest of the four, we selected 4 special angles, which I will get to. The line labeled D still has not even, the shock has not even started to really accelerate and take off. Nothing in front of the quote unquote shock front has yet been accelerated.
Right.
Whereas line A has already broken out. Line A, it's maybe easier to see up in the temperatures. Line A is the thin line. So if you look at T3 and then the thin but dark line up here, yeah, that Frank is highlighting, it's already starting to leak out some of its radiation, heat up the gas in front of it, even 4 hours before the peak of the light curve.
Okay, and just to be clear here, you get different radial profiles. That's what each of these lines are, and that's because the envelope is convective.
Yes, that's because the envelope is convective. So I guess maybe I should have said, and this is actually probably the next. Let's go 2 figures from now.
Okay.
I think it's figures, or 3 figures from now. Figure 8.
Figure 8.
Yeah. So here's figure 8, which I think may make this a little bit clearer, or even. So one of the main differences between one of the things that we found, and also that was found by Andrea Chiavassa, the other and the other group that have 3D simulations of red supergiant envelopes, is that in red supergiant envelopes, the convection is really large scale with really big density fluctuations. And unlike the sun, which has millions of or billions of tiny granules, tiny, which they're the size of the US state of Texas, but the sun is much bigger than the US state of Texas. So at the surface of the sun, the sun is very spherical. You have all of these tiny little convective bubbles. In a red supergiant, the size of the plume is of order the radius of the star.
Okay.
And so you have these really large scale convective bubbles. So instead of being like a bunch of tiny little bumps, it's like this bulbous surface with maybe 8 plumes spanning the entire star.
Okay.
And that leads to this spread. So here's density, and then the bottom, the lower panel is optical depth uh, along a line of sight inwards. So
Yep.
each of the radial profiles, A, B, C, and D, the special ones, are labeled here just to give a sense of what the spread could be. So A we think of as a valley, D we think of as the peak of a mountain. There are different profiles in the density along each of those.
Absolutely.
Um, and it's actually worthwhile to note the two blue lines
Okay.
are 1D models.
Yeah. Okay.
So the differences between the 1D and the 3D models
Yes,
are,
please.
one, that the 1D photosphere is at higher densities than are achieved in the 3D models.
Okay.
So that means that the bottom edge of the blue curves
Yes.
are um,
Very
are higher up than in this plot than the spread.
yes.
The colors here, the red colors indicate what is the likelihood that you find a fluid element at this radius that's at this density. So a
Okay.
vertical slice is at constant radius, what's the spread? It's a histogram,
Mhm.
what's the spread? And
Yes.
then a horizontal slice is
Yes.
for a given value of the density or a given value of the optical depth, what radial span is that?
Correct. I'm with you. Very good.
Um, so for this particular one, if you slice through it, um, you can get something like 80 solar radii of spread for what we would consider the surface of this star, or for what we would consider the region
Yes. It's
where
about
the shock is going to break out.
good. Okay. Wow. It's gonna make it
Yeah,
hard to tell a temperature.
it's going to make it hard to tell a temperature. It's going to make it a lot of things. So, all right, and so actually, um, the next figure. So, uh, I should probably mention that there is actually an expectation for where in the star the shock will break out. And this happens,
Yes.
so you have a shock that's containing a whole bunch of energy and radiation. That shock wave travels through the envelope. At some point, photon diffusion will be faster than the shock is traveling. That happens at low enough optical depths that the photon can escape.
Mm-hmm.
Uh, that can be expressed as where the optical depth equals the speed of light divided by the shock velocity.
Yeah, good. Okay.
So if the shock is moving at 3,000 kilometers per second, the speed of light is 3 by 10 to the 10 centimeters per second. Doing the conversion in your head, that gets us to an optical depth of about 100
Yes.
is where we expect the shock to break out. So if
Okay.
we drew a horizontal slice through the lower panel is the optical
Okay.
depth.
Yeah, let's
So if
do
we
that.
draw this horizontal slice
About 100.
and then go to the next figure, I'll
Okay.
show you that horizontal slice is where we expect shock breakout to happen. What is the radial span of that, and what does this surface look like?
Okay.
So figure 9 shows that rough, hand wavy expected shock breakout surface. And notice that this is cosine of theta
Okay.
versus phi. This is phi is the azimuthal angle around the star.
Mm-hmm.
Cosine of theta is the copolar angle,
Okay.
or it's the cosine of the copolar angle.
Mm-hmm.
Um, or maybe it's just polar angle. Either way, uh, the the box is a region that we zoom into for other figures. Points A, B, C, and D are labeled.
Nice. Okay. Now I get it. Mm-hmm.
So A is a valley. I probably should have led with this.
Right.
A is a valley, B is the side of a mountain, C
Yeah.
is kind of on a plateau, and D is the peak of some really large mountain. The darker colors correspond to stuff where this surface is deeper in.
Yes.
The lighter colors correspond to the stuff that's at the top. And so we expect if a shock wave stays spherical, then it will hit A first, then it will hit B, then it will hit C, then it will hit D as it's plowing its way outwards through the star.
Makes sense. Okay.
Yeah.
Very cool. Look like granules on the sun.
They look like granules on the sun until you realize that this is not a tiny patch of the sun. This is the entire star,
Right.
or almost the entire star.
Mm-hmm. Very cool. Okay.
Yeah.
All right.
So,
Okay.
right. So then going back to the previous section, we spent we spent some time thinking about to what extent do the fluctuations as it's propagating change things.
Yes. Yes.
And so figure 7, I think, shows how those particular inhomogeneities grow.
Okay.
So we inject the shock, or we deposit the shock down at 500 and or we deposit the shock down when the shock is at 450 solar radii or so.
Yes.
We let it travel to 500. The inhomogeneities don't really do much at that point.
Okay. Okay.
The surface, I should mention that the surface that breakout is expected to happen
Very good.
is out at about 820 solar radii,
Yes.
plus or minus 80, or plus or minus 40, I guess.
Okay.
And so then at a later time, the shock. So this is maybe a complicated figure, so it might be worth actually explaining what the different axes are. The left column are the radial coordinate of the fastest moving fluid element along each line of sight.
Yes. Relative to the average.
Right, relative to the average.
Yep.
The middle column are the velocities, also relative to the average. And then the right column are the temperatures, also relative to the average.
Oh,
and
valley, hill, plateau, mountain.
Exactly, valley, hill, plateau, mountain. And A is expected for the shock to reach it first. B is expected for the shock to reach it later. The fluctuations go. The fluctuation axis goes from plus or minus 15%. The radial coordinate of the shock actually never reaches fluctuations that are that large. It only reaches fluctuations on the order of a few percent, until it starts to get really close to the surface, which isn't shown in this figure, but it will be in the next.
Right.
The velocity spread does increase. So if you give it enough time, if you have a big velocity spread, then you'll have a big radius spread, but there is not very much time. And then similarly, there has this growing kind of 10% spread in the temperatures at that shock front location throughout it. But maybe like it looks, and you can see the imprint of that convective granule like pattern on these properties as well.
Very good.
Okay. So now go, and I guess the one other thing is to show, maybe it's just worth saying in words. There's another figure that argues that most of the motion is really radial. So we don't see a lot of obliquity in the shock breakout. We don't see a lot of that. It's mostly a radial shock that's plowing through this thing with some level of fluctuations. But there's these large fluctuations in the surface that it's going to hit.
Yes.
And that
that
matters. Okay.
Very nice.
Very nice. So so then maybe before I go on to what we actually see happen, it's worth stating what we expect to happen in a 1D model.
Okay.
And for that, I think it's really helpful to think about timescales. And the first timescale to think about is the diffusion time, the photon diffusion time, how long it takes once that shock reaches that optical depth tau of the speed of light over the velocity of the shock. How long will it take photons to get out? And in a typical 1D stellar evolution model, the answer is tens of minutes to no more than an hour, depending. And that's, I think it's equation. It's equation 2. Yeah, equation 2. So equation 2 is the diffusion time. It's related to the speed of light. It's related to rho naught, which is the density of the material, and the shock velocity squared. It's the thickness. It's the thickness of the layer divided by the effective speed of photons, which is c over tau, which can be expressed in terms of the density there and the shock velocity. And this is in the 1D picture
Mhm.
of a sphere. So
Yes.
that time scale is, again, typically tens of minutes.
Okay.
There's another time scale in 1D models, which is highly sought after because it gives us a direct constraint on the radius of the star, and that's actually the light travel time across the surface of the star.
Okay.
So if you have a perfectly spherical breakout in a really big star,
Okay.
then here's the surface. I the observer am standing on the top of my head. Uh, if it all breaks out at once, I will see the stuff that breaks out, on along the line of sight
Yes.
first, and then the radius of the star divided by the speed of light time later, I will see stuff from the limbs of the star. So
Yes.
because light from the edge on part doesn't reach us at the same time, that if that time scale is longer than the diffusion time,
Okay.
then it smears out the shock breakout over a duration that is the light travel time of the star.
Yes.
So if this time scale
Right.
is bigger than, and in a lot of 1D models, these timescales are comparable. So
Okay.
for 800 solar radii,
Okay.
this is about half an hour.
Okay.
And if the diffusion time is a couple tens of minutes, then we're in business. We can launch UV satellites up to measure the duration of this thing, and then get a radius of the star. Uh, you know, you need pretty high cadence to do it because you're trying to measure something that
All right.
changes tremendously over a time scale of half an hour, but uh,
In principle.
in principle, it's measurable in the 1D picture.
Yes.
So those are the two time scales,
Okay.
and thinking about the hierarchy will tell you roughly how long it'll take the light curve, the light that you see, to either rise and reach its peak, or how long it lasts, basically.
Yes. Peak and valley.
Um, But in the 3D case, there's one other there's one other time scale that I think sorry. There's one other time scale that's important, which is the crossing time of the inhomogeneous outer layers, or the time it takes the shock from once it hits the valley to then
Oh,
hit a peak,
okay. Okay.
or from once it hits a valley on one part of the
Yeah.
star to hit a peak on another part of the star.
Yeah.
And that time scale can be
Communicating.
expressed as delta R, this new quantity that measures the level of the radial span of these large scale fluctuations,
Yes.
divided by the velocity of the shock.
Crossing time for the region. Yes.
And that time scale for a delta R of about 80 solar radii and a shock velocity of a few thousand to 5,000 kilometers per second gives us something like 3 to 5 hours,
Right.
which is unfortunately much larger than the light travel time across the star.
Yes. Yes.
And so this is,
Yeah.
yeah. So in terms of our expectations for what will the duration of this breakout pulse that we see in our 3D models be, we think that the crossing time would be the best measure, or the best thing that we could extract from the duration of the pulse. So this is our expectations. This is our expectations both going into it and motivated by it. I've seen the answer. I can tell you that's what it is. And if you read the paper, you can see it too. Um, so now let's scroll up. So with those time scales in mind, let's scroll
Right.
up. So
Okay.
the other thing is, there's one other really important thing, which is because we reach lower densities, we also get longer diffusion times.
Uh,
Uh, so if you look at equation 2, there's a density in the denominator, which means that lower density leads to a longer expected time for even photons to escape, because basically the envelope is fluffier. So I like to say it's bumpier than it is fluffier, and it's fluffier than it is big.
there you go. That is a great analogy.
Yeah. So we can look at figure 10, actually, now. Now that we have that in mind, we can look at figure 10, which takes a handful of snapshots. I should mention the diffusion time is about something like 1.2 hours.
Okay.
Um,
Okay.
and so in 2.4 hours before the peak brightness, we actually already have some, the colors on this are the radial velocity. This is now a horizontal slice through the star. The
Hmm.
thatched area is our simulation inner boundary.
Yes.
Um, the dotted line is roughly
Oh,
some spherical approximation of where the photosphere might be if you said L equals 4 pi r squared sigma t to the fourth.
let's say we do that. All right.
If
There.
you say assume the Stefan Boltzmann equation, then that's roughly where we would say the photosphere is.
Okay.
Uh,
Okay.
so the sphericalization of it. But you can see that um, stuff getting accelerated is roughly synonymous with the stuff breaking out.
Yeah. Hmm.
Um, and so you can
Bing.
see here around actually where there was this really significant valley, you see this really bright accelerated uh, hotspot.
Yes. Right there. Right there.
Right. And
Right
then
there.
as time goes on, you see
Uh-huh.
hotspots appear on different parts of the stellar surface.
Mm-hmm.
Um, and or hotspots, bright spots, fast spots, whatever you want to call them. So another way of visualizing this is the next figure.
Okay.
I
Very
think
cool.
it should be the next figure, or yeah, it should be the next figure,
Uh-huh.
which is this is a huge figure. This is now take that previous figure that I discussed with the fluctuations, but
Uh-huh.
these are now absolute coordinates, and these are just times very close to the shock breakout.
Okay.
So this is the radius of the fastest moving fluid element in units of solar radii.
Mm-hmm.
This is the radial velocity in units of 1,000 kilometers per second.
Yes.
This is the temperature of the material. So you can actually see that, and then each of the rows is a different time snapshot.
Yes.
This is
Yeah. Two.
this is a projection of a surface, and then time lapse of that. And I'll get to the fourth panel in a moment, but I think it might be helpful to stare at the temperature column, the third column, the T fast.
Yes.
Um, and you can see that even at negative 3.5, even at 3.5 hours before the peak brightness, uh, some of the stuff has already been hit and started to radiate. So now let's go to the right panel. So if you look at A,
Okay.
it's considerably cooler than the temperatures at the rest of the material.
Yes.
And that's because it has already, radiation is already leaking energy out of the shock front there.
Okay. Uh-huh. Sure.
And you can even see that a little bit as
Right.
a blip. The
Yeah.
right panel is a scaled flux.
Mm-hmm.
So it's equivalent to what is the luminosity at that part of the star.
Yes.
I, the observer, would be seeing this whole thing, so I'd be leaning back and squinting. But um, the if I put my eyeball up to the star that's exploding, which you should not do, you
Safety
would see a
method.
little bit, yeah, around A, and then around this crevice between the
Right.
plume that held
Right here.
houses B and the plume that houses C. You can see a little bit of light already starting to come out of
Yeah.
more than 3.5 hours before,
Cool.
and that light,
Yeah.
that those regions grow, and then as so if you look in the next panel, then you can see where the temperature is lower. It means that the radiation has started to carry some of that energy, some of that heat out from the shock front. And
Mm-hmm.
you can see that correspondingly in the flux where you put your eye too near the photosphere, or
Yep.
this photosphere is a different, it's a different criteria, but that's a detail. Um, and you can see as the shock travels through. So if you look at the point labeled D, even down at 0 hours, which corresponds to the peak in the brightness,
Right.
it still is able to retain most of its heat, and it's not as bright as the stuff around it. So
Right.
you have, and you can even see stuff that is undergoing shock breakout, that it's having its shock breakout many, multiple hours after the first time the shock hits
One.
anywhere on the star.
Yeah.
So that the the lightest colored stuff on the left panel, what, if you ask what is the lightest colored stuff, well, that the location of that lightest colored stuff moves, around the surface based off of what is undergoing shock breakout right now, what
Right.
has already cooled. So you
Right.
can see this really hot spot at negative 2.4 hours, or this really bright spot, or this really fast spot.
Mm-hmm.
uh It stays fast, but it cools down. And if you look, that like that light colored blob at 2 point, the lightest of the material at negative 2.4 hours is actually some of the darker material at 0 hours.
Correct. Yep. Yep. It's radiated.
Yeah, because it's radiated away and already started to cool.
So
so the picture that emerges is a lot more complex than a spherical breakout that the spread, that might get smeared out by the light travel time across the star.
Yes.
And rather is, a bunch of patches, valleys getting hit, then the hillsides getting hit, then the plateaus getting hit, then the mountains getting hit, over a time scale that is how fast is the shock moving, and how thick is that outer, how mountainy is it? How high are the mountains compared to the valleys?
Correct. Delta R.
Yeah. What is this delta R?
Mm-hmm.
So another prediction is that at any given time, we might, and this is stuff to explore further. My printer has decided to
print
pages at me that look like, I think I'm out of black ink. That's weird. Anyway, what was I saying? So one prediction is that at any given time, if I was to lean back, squint, and ask, well, how hot are the photons that I'm seeing? Because I'm seeing, the answer is that there actually probably would be some spread in that.
Yes.
So that's what the next figure shows, a T-tau relation.
Yeah.
The temperature, and this is taken, I think, at the time of the peak in the bolometric luminosity.
Okay.
I keep talking about this magical time of the peak bolometric luminosity, and I haven't even shown the figure that is the light curves. But
the peak.
Yeah, and this is very much a theorist plot.
Right.
It shows what is the relation that you would expect for a gray atmosphere. The arrows actually are a shock temperature of the explosion energy, and that's analytic. So this is what would we expect this to asymptote to. And we're really happy to see that analytically our expectations agree really well. That the temperature behind the shock matches based off of the properties of the stellar model, and the explosion energy ends up matching very well with our expectations. So that's another kind of vote of confidence in the rest of what we're seeing. Is when things agree where you expect them to.
Very good.
And then the shaded spread for each of these corresponds to what is the spread in 80% of the solid angle. So 80% of the lines of sight you could see, what would they tell you? What is the spread in the answers they'd tell you for the T-tau relation along each of those lines of sight? And so that's, so what we predict that we don't have the tools quite yet to answer is that the photon spectrum might actually be smeared out. Because you're seeing different stages of shock breakout all at the same time within that 6-hour span.
So these are the spreads. Yes.
So these are the spreads. So now let's go to figure 13, which are the actual light curves.
Ooh, actual light curves. Summary of the models there. Okay. Yeah.
So So summaries of plot properties of these light curves are given in the table. The explosion energy, the ejected mass, the radius, and then the brightness, how long it takes to rise from the half luminosity to the peak of the luminosity.
Okay.
And then delta T1/2, which we characterize the duration, which is the time it takes to get from half brightness to peak brightness back to half brightness. So I'll note that the rise times here, and maybe I'll note that the rise times here are actually kind of an underestimate in terms of these particular rise times labeled here are sort of an undercharacterization, I should say, of how long it takes to go from nothing to peak brightness.
Oh, sure.
Because it's how long it takes. We're hoping that this is a little bit more useful for observers.
Right. Once you get to polling, what is that rise time? Not
exactly.
hours before.
To half brightness to peak brightness is something that might be measurable.
Right.
Nothing to peak brightness is
Mm-hmm.
really hard to say.
Mm-hmm. Sure.
But so the light curves now are shown in this lowest in figure 13.
Very nice.
And so here, the upper panel, the black line is the fiducial model that we've been considering, and that's so we show log brightness on the top panel,
Yes.
and then and then linear brightness on the lower panel.
Okay.
Each so now I take an observer, I put them sufficiently far away from the star that I think that my observer can squint and see the whole star,
Okay.
more or less.
Yes.
Or at least see most of the star. Uh, the the black lines are the same between the two panels. The upper panel now shows variations in models. So we did this not only for our for the fiducial explosion, but also for a different 3D red supergiant envelope that we simulated that has a larger delta R but a lower ejecta mass. So actually, weirdly, the time scale, this delta R over V shock, actually kind of matches more or less, which is why the durations are fairly similar. But the shape, you'll notice, isn't similar between the two rises, and that's because because of the plume geometry, because the orange model is a bulkier, more bulbous surface that kind of has one really big crevice, and then some mountains with mountains on top, basically.
Much more than.
And then two 1D explosion models, which from a different from one of our other works, are there, and you can actually measure the width of these peaks kind of from half to half, and the width is really agrees very well with R over C, with the radius over the speed of light.
Okay.
So if things were like the 1D models, then we could measure that. We could say, okay, well, here's the duration. The radius of this star is 850 solar radii for the dark blue case.
Yes.
So R over C is about half an hour. We see half an hour spread in this. Oh, everything agrees.
Everything would go good. I'll go home happy. Okay.
Right. We can all go home happy. And then we know the radius of the star that exploded, which I have a vested interest in knowing the radius of stars that explode, because I think that allows us to tell us a whole lot more information, which is maybe a plug for some of my other work. Also published in the Astrophysical Journal.
Well,
but yeah, so
models, there's a lot of spread here.
Yeah, so there is a
yeah, there's a lot of spread. They're wider, than the 1D models.
That's right, and they're fainter, notably.
Yeah.
So the 1D models peak at almost 10 to the 45 ergs per second. The 3D models peak closer to of order 10 to the 44 ergs per second. This can be thought of as a function of the fact that the luminosity, a characteristic luminosity, and I think this is equation 5, a characteristic luminosity is equal to roughly the energy contained. I think it's up. Oh, there it is. No, you got it. Roughly equal to the energy contained in radiation at that shock breakout surface, in that layer, sort of outside of which the photons are diffusing through, divided by how long the shock breakout lasts, or divided by a relevant time scale. So a lot of the literature will say that the characteristic luminosity, or the peak brightness, really, is equal to this E naught, which is roughly the same in the 3D picture versus the 1D picture, divided by a diffusion time.
Sure.
And when you get that, you actually get a scaling with the stellar properties, including the explosion energy.
Okay.
But when you say that time scale is the crossing time of those inhomogeneous outer layers, you'll get a different explosion energy scaling.
Yes.
And that explosion energy scaling is what we is in much better agreement with what we see in the 3D models.
Okay. Mm-hmm.
So when we explode it with multiple energies, which were the lower panels on those light curves, we get better agreement with this, with the idea that this is the relevant time scale, that the crossing time of these layers is smearing out things.
Got it.
And so if the crossing time is longer, then E naught over the crossing time is fainter.
Yes. Uh-huh. I'm with you. Very good. Okay. So what does this tell us about being able to, since that was an interest of yours, of extracting radius?
Yeah. So what it tells us is that unfortunately, the level of surface fluctuations matters, and is in many cases there are regimes where this may or may not be true, but in the fiducial case, or in a typical case, we expect that the time scale to be dominated by the level of surface fluctuations. So in terms of prospects for measuring the stellar radius via light travel time effects,
Yes.
I think that unfortunately is going to be
Challenging.
going to be challenging, or at least impossible, in a star that looks like these 3D models.
Okay.
If the stars don't look like these 3D models, then there's
That's something different.
maybe there's hope.
Okay.
Similarly, it would be hard to get a constraint on the diffusion time when the crossing time is longer than that time scale as well.
Yes.
Because the diffusion time also, maybe, okay, because the densities are lower, the diffusion time is a little bit less. It's not there. Yeah, the diffusion time is still a little bit less than the crossing time in
Okay.
these models, but they are
Oh,
not an order of magnitude different. They're a
okay.
factor of a few different.
Okay.
So there are, um,
Cool.
but the thing that I think is really exciting is the fact that because the level of inhomogeneity in the surface layers imprints itself in the light curves,
Yes.
that means that the light curves give us
Uh,
a
uh,
tool, or
yeah.
give us at least a path forward. Maybe more theoretical work is needed, but give us or just a wealth of observations are needed, which hopefully we'll have soon with the launch of Ultrasat,
Yeah.
which is Israeli launched or NASA launched Israeli led mission to look at hundreds of shock breakouts in the UV. So in terms of prospects for Ultrasat,
Yes.
uh, it would be good to have a spectrum so that we can take a bolometric luminosity from our models and then turn that into predictions in the actual passband.
Mm-hmm.
But we're near the peak. The temperature is comparable to the passband wavelength,
Okay.
meaning that we expect roughly our predictions for the duration to be both the same in bolometric and in the UV. But in terms of so prospects for that are that the 3D shock breakouts we expect are a little bit fainter, but they are longer. So maybe maybe we don't need that 5 second cadence or 5 minute cadence. Maybe we can get away with a little bit, not 5 seconds, but
Yeah, forget
yeah.
it. Very
But
cool. Very nice. Very nice.
so yeah, so maybe a wealth of observations would act, or would actually give us like a characterization of how much the radii of red supergiants fluctuate
Yes. Yes. Yes.
amongst, like, individually amongst themselves, which I think is really exciting. It's
Yeah.
it's always fun to identify something new that you could probe that you didn't that we didn't have a way to probe before, or that the only way to probe before was like ALMA images, or finding the 3 red supergiants nearby that we could actually point spectrointerferometers at and get tomography or something like that, which is also really cool, exciting work in and of itself.
Yes. Don't want to put that down, but
Oh yeah, no, everything's everything's cool. There's so much.
very nice. Very
And I
good.
guess one other thing that's kind of nice is that there have been a few detections, maybe 3 or 4 serendipitous galax detections of ultraviolet shock breakout,
Yeah. Mm-hmm.
and all of those show timescales longer than the 30-minute R over C. all of those show something more like 6 hours.
Okay.
And that's often attributed to a dense wind. Uh, so there's still work to distinguish like what is the difference between a dense wind and a fluffy, bubbly outer envelope
Yes.
that we see in our 3D models. And
Awesome.
maybe they are saying something similar, uh, or that a spherical dense wind looks like a bumpy, fluffy 3D outer envelope.
Right.
Um, but that's that was the yeah.
Very good. Awesome. Jared, thank you so
Yes.
much for walking us through this very lovely article.
Thank you.
And you touched on it a couple of times.
Mhm.
So let me ask it this way. Where do we go? Let's say over the next 2 to 5 years, or one's next postdoc, as the case may be. Are there additional models that are being run, or are you considering lumpy circumstellar medium, so you can disentangle between what's going on at the photosphere and what's going on in the wind? You already mentioned some of the UV sat stuff coming up, so that's good. So just kind of where do we go with this topic, new topic, I will say, over the next couple of years?
Yeah, no, it's a great question. As Axl Rose asked, where do we go now? Um, for the three Guns N' Roses fans who are in the audience, but the
Very good.
so the first thing I think it would be really useful to have a good way in the 3D models to capture what we expect the spectrum, or at least the SED to look like.
Yes.
Um, and
Yeah.
that's underway. We now have the capabilities. I'll give a plug for work that is very much in the preparation stages, but we now have the capabilities to potentially get to do multi-group radiation transport with Athena. Yanfei has spent a lot of time recently writing with his fast rad hydro scheme also to do that in multi-group. And so hopefully we will be able to answer that question of like what is actually how much does the spectrum smear? How does that push, where does that smearing push stuff? If it cools it down, maybe that's actually a good thing for
Yeah.
ultrasat, because even though these shock breakouts are fainter, if we see more at time of peak brightness, if we're seeing more stuff that is a little bit cooler, then that's actually a good thing, because the ultrasat band is a little bit redward of the peak in the bolometric luminosity, or I should say, a little bit redward of what you expect the peak temperature to be.
Fair enough.
So that would be great.
Very cool. And
Um,
when does that satellite launch? That's not long?
2024, 2025. So
Yeah.
it's still a few years out, which means that, for me it's good, because it gives a little bit of time to motivate some of the three, to actually conduct the theoretical work that I think will be important. And there are a lot of people thinking about how to make the most of this amazing instrument that we're going to be launched.
Yeah.
And there's a lot of great work out there.
Yeah. Well, now is the time to get your predictions up, right?
Exactly.
So you got a few years to get your predictions up. Very cool.
Yeah, a few years. And then the other thing, so down the line, there has also been work thinking about shock breakout in circumstellar materials. Most of that work is also with 1D, either 1D models or stuff. Benny Zhang actually recently published a paper, not of shock breakout or anything, but just of what does circumstellar material look like if it's created by by sort of a pre-supernova outburst. And if that was from a 1D star or a 3D star, and there are differences between the 1D and 3D cases, which means that I'm interested in maybe seeing if I can generate a little bit of a 3D circumstellar material from my 3D or from these 3D stellar models, and then possibly running a shock breakout through that. That would be another interest, or a shock breakout, or the first 10 days of the light curve. Those also, the shock cooling phase also has additional information, not just the first hours, but maybe the first days. Looking at that too might be interesting.
Cool.
And then
cool.
more models, more more computing time, more any of that. But And then looking at other systems. But I think the most immediate, like, what would I really like to know if I could have one thing that
Yeah.
I needed to know now, I would want to know what the spectrum looks like.
Yes.
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 Or not even the spectrum is going to be probably some kind of blue continuum. What does the
Well,
SED look like? The other thing, although there's observations of flash spectroscopic features, so lines outside the photosphere that are excited by the
oh,
oncoming
right.
ionization
Yeah, yeah.
that give you a handle of the temperature of that. So maybe
Yeah.
there's a lot of debate on how much flash, how ubiquitous are these flash features? Do they necessarily tell you that there's a lot of circumstellar material that will contribute energetically to the light curve, or do they tell you that there's a little bit of fluff placed there or something like that?
Yeah.
Um, but that being said, they do give you a handle on the temperature. So maybe, I also want to see, like, if I could way down the line not just get multi-group but get an actual spectrum of this, then do we naturally get flash features, or would we really need a circumstellar material, some fluffy
Yeah,
thing
that'd
to
be interesting to know that.
explain it?
Mm-hmm. Mm-hmm.
And a million other interests and related questions. And then if you can,
It's a rich topic. It's a rich, rich topic.
yeah, it's a
Lots of
rich
fun.
landscape of stuff.
Very
But
cool.
that's part of what's exciting about all of this, is it's all connected.
Yeah, yeah. And I definitely look forward to over the next couple of years as we see this next generation of models come out and a new satellite going up that'll probe it. It's going to be very exciting. And I look forward to seeing the development over at least one postdoc.
Yeah, thanks. And I'm honored and excited to be able to
Be
keep
at the
working on it.
forefront. Yeah, very
Yeah.
cool. All righty. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.
Thank you.